So differential scanning calorimetry. Watch closely. This thing is a little bit difficult to understand because we are not familiar with uh, the differential scanning calorimetry. Here we are having two substances. One is the test sample, and the other one is a reference substance. You are going to maintain the temperature of the temperatures of the test sample and the reference sample the same, which means that you are going to maintain the temperature difference between the sample and the substance zero. So the transfer of heat to the substance or from the substance is made to maintain the same temperature between reference and the sample. So that is the principle. So the principle you have to be very clear. You are going to supply heat energy to the substance, or you are going to take away the heat energy from the substance so that in the given environment, the substance and the reference are in the same temperature. The main application of this differential scanning calorimetry is that you can study the actual happening in the polymers and in other samples while heating. What is happening when the temperature is raised in the polymers? What happens in the other samples? That mechanism can be followed by this differential scanning calorimetry. Actually, it is not going to reveal the actual mechanism which is taking place inside the samples, but it will give you only the quantity of the additional heat energy to be supplied or the heat energy to be taken off from the sample to maintain the same temperature with the reference taken. So this knowledge, what you are actually doing, it is giving you the enough information to understand the mechanism of what is happening in the polymer and in the sample. Say, for example, melting of a crystalline polymer. Normally, the melting of an amorphous substance will take place in a range of a temperature. But the melting of a crystalline substance will take place exactly at a particular temperature. You may be knowing the reason. The amorphous substances, they have varying linkages between the molecules. So which is the weakest one will be broken first, and a little bit stronger will be broken next, and then the strongest will be broken at the last. So you cannot mention any sharp melting point of the amorphous substances because it melts in a range of temperature. But crystalline substances, as they have a regular pattern of arrangement, the bonding between every molecule is similar. All the bonds break at a particular temperature, so the melting is very sharp. So such melting can be understood, can be followed using this differential scanning calorimetry, melting of a crystalline polymer. And also in crystallography, you might have studied a very important concept called glass transition. There is a temperature called glass transition temperature. It can also be followed using this differential scanning calorimetry. and also the crystallization procedure itself. Some crystallization will take place at an elevated temperature, and also excess amount of heat energy has to be supplied for the crystallization. So in such occasions, when you keep a substance which is to be crystallized and the other substance as the reference and put together, additional supply of heat energy is required to the sample pan to initiate the crystallization and for proceeding of the same. So such additional supply of heat energy for the crystallization can be followed using the differential scanning calorimetry. So now another important application. Look here, this is the block diagram of the differential scanning calorimetry. So there is a closed environment, and in the closed environment, this is called the reaction chamber. There is a pan. This is called a sample pan. And what is there in the pink color inside the pan is the polymer sample. And on the other pan, there is a reference pan. Normally, we do not keep any substance in the reference pan. The reference pan, empty reference pan itself is the reference. And another thing is the heating rate has to be in a particular rate, say 10 degrees centigrade per minute. In 1 minute, you can raise the temperature 10 degrees. Suppose at this minute, it is 20 degrees centigrade, means in 1 minute time, it has to rise to 30 degree, 20 to 30, 10 degree rise. The rate of heating is very important because the sample pan needs more heat, whereas empty pan needs less heat. See, you are supplying heat energy to both the pans simultaneously, but when you note down the temperature rise in the empty pan and in the sample pan, according to the concept of heat capacity, what is the quantity of the heat energy required to rise the temperature of a body by 1 degree? The sample pan will need more heat energy to rise the temperature, whereas the empty pan needs less heat energy to rise its temperature. But you are going to maintain the temperature difference is zero. So the rate at which the heating is done, it is very important. And after doing this, actually there are recorders which are very accurate and precisional recorders, which will continuously record the temperatures of the sample and the reference as a function of the time or as a function of temperature. Suppose if the temperature rising rate is kept constant, then you can record the temperatures of the reference and the sample as a function of time. Suppose temperature increase varies, means you can do it with the temperature also. So the plot or the graph to be drawn for this experimental technique is that the temperature is taken in the x-axis and the difference in heat is taken in the y-axis. That difference in heat is actually measured as the output difference of the two different heaters employed to heat the sample and the reference. So you should understand these things very clearly. In the x-axis, the temperature is taken. In the y-axis, the difference in heat. Actually, the difference in heat means it is not near the temperature, it is the output of the two heaters. Because it is calorimetry, this is not a thermogram, it is calorimetry. What is the quantity of the heat energy supplied by the heaters to rise the temperature? See here, the temperature is not important. What is the temperature difference? That is very important. So the output of two heaters, how these two heaters outputs differ from each other. What is the quantity of the heat energy to be supplied to rise the temperature of one particular substance and the reference, so that the temperature difference is always zero. So that is very important. So another thing, there are two types of differential scanning calorimetry. One is called compensation differential scanning calorimetry, and the other one is called heat flux differential scanning calorimetry. Look here, in the case of a compensation differential scanning calorimetry, you can see the block diagram. See, this is the sample pan, and below the sample pan, there is a sensitive sensor, and below the sensor, there is a heating wire. This is a resistance wire, which is a part of the heater. When electricity passes through this wire, the wire will get heated up, which will be sensed by the sensor, and the actual quantity of the heat energy supplied to rise the sample is noted down. And in the other chamber, there is another pan, which is the reference pan, and there is also a sensor, and there is also a heating element. Now, what is the quantity of the heat energy supplied is also measured, and the sensor is continuously recording the temperature, and the care is taken. The temperature difference between the substance and the reference is always zero. So this is one type of setup, which is called the compensation differential scanning calorimetry. And the other type is called the heat flux. What is this heat flux? Look here, the heating block is a common, but the chromal wire that is connecting the sample and the reference, you can vary the temperature of these two, or the quantity of the heat energy supplied using these two. And there is a chromal disk, and on the chromal disk the substance is resting, and also here the reference is resting. So the heating is a common, but it is diverted in a different percentage to these two substance and the reference, so that the temperature will be maintained the same. That is, the temperature difference is always zero. Now, the various substances by which the sample holder can be made are aluminum and platinum. Normally, the substances chosen are supposed to have the following characteristics. Number one, they should withstand a high temperature. Number two, they should have very less heat capacity. They themselves should not absorb heat. And number three, they should be non-reactive and non-corrosive. Number four, they should not get decomposed. That is stability, resistant to heat. So these are all the important characteristics that they should have to be a sample holder. And the other part of the differential scanning calorimetry is the sensors. Normally, platinum resistance thermocouple sensors are used. See, what is a thermocouple? Two conducting material of a different temperature coefficient. When they are connected together, the junction point is called a thermocouple. When this thermocouple is kept at a higher temperature and the other thermocouple is kept at a lower temperature, there develops a voltage between these two thermocouples, and depending upon the voltage and the temperature difference, it can be calibrated. So here what we are using is the platinum resistance thermocouple, which is used as the sensors in the case of the differential scanning calorimetry. And also the rate of rise of the temperature is controlled by a programmer, a computer programmer. Actually, the role of the programmer here, it is taking care of maintaining the rate of heating a constant. Otherwise, what will happen if your rate changes? The rate of your supplying the heat energy and the rate of accumulation of the heat energy by the sample are supposed to be equal. Otherwise, what will happen? the temperature difference will not be accurate and nothing can be interpreted using the data obtained by the differential scanning calorimetry. See, the main business is here. You are not simply measuring the temperature difference, you are very much concerned about the quantity of the heat energy supplied in Joule. So, what is the heat energy supplied? Calorimetry. So, the temperature controller is a very important part of this system, and also the programmer, the computer programming system plays an important role in controlling the temperature and in controlling the rate of heating of the substance. So now, first of all, you have to evaluate a baseline. What is this baseline? The thermal resistance of the sample and the reference sensors are to be evaluated. First of all, the baseline is only for the sensors. Without keeping the reference or the sample, you are going to evaluate in the full range of the temperature in which you are actually going to do the experiment with the sample. Suppose I am choosing a temperature range from 100 degree to 500 degree because I have already studied that the sample that is to be tested undergoes some change at around 300 to 400. So I am choosing a temperature range of 100 degree to 500 degree centigrade. First of all, this temperature rise has to be given to the instrument without the sample and the reference so that the sensor baseline can be evaluated. So this is the baseline. You can see in the graph, the dotted line. Actually, this is a straight line like this. In this place, the actual substance goes up. Therefore, the baseline is beneath. So it is marked as a dotted line. So this is the baseline. So step 1, temperature difference between two empty crucibles is measured. Step 2, the thermal response, the reference material and the substance taken, they are measured. Normally the reference material used is the sapphire. So if an exothermic process is taking place in the differential scanning calorimetry, you will get a positive peak. The peak goes up and then comes down and then it sets in with the baseline. Suppose if no substance is kept, you will be getting a straight line like this. Like this. Actually, we cannot say this is a straight line, but it is an approximate line like this. So when an exothermic process is taking place, you will have a peak going up and then coming down like this. So sapphire is the reference material which is used in the differential scanning calorimetry. You can see the phi m, which is the difference in temperature between the sample and the reference is taken along the y-axis and the temperature is taken along the x-axis. So this is how the differential scanning calorimetry is recorded. Now look here, temperature. When melting is onset, the temperatures are furnace thermocouple in order to understand the behavior of the differential scanning calorimetry. First of all, it has to be experimented with the substances whose melting points are well known. So melting points of a standard substances is known and that substance is taken which is kept in the differential scanning calorimeter and then it is studied. So this is called a calibration of the instrument. The previous class itself I have told you number of examples for the calibration. Some unknown instrument is calibrated using a known instrument. Suppose if you are having a straight stick which you want to use as a scale, take a real scale and mark accordingly by keeping the scale and the stick together. Now the readings can be marked in the stick, and then after you can use the stick as a scale for measurement. This is called calibration. Even when you studied the bomb calorimeter in the second year, which is used to find out the enthalpy of a combustion, you just calibrated the instrument with the benzoic acid, because benzoic acid molecular formula is known, and benzoic acid uh, enthalpy of combustion is also accurately known. So you are putting that, and you are finding out the water equivalent of the calorimeter. So this is called calibration. So here also, in order to calibrate the entire system, you are taking the substances with a known melting points. So what are all the characteristics of expected? What are all the expected characteristics of a calibrants? Number one, the substance is supposed to be of high purity. Number two, its enthalpies should be accurately known. Number three, the substance has to be thermally stable. Number two, the substance has to be light stable. Light stable means it should not undergo any photochemical change. Number four, it should be number four, it should be, number five, it should be non-hygroscopic. I have already told you what is hygroscopic. Hygroscopic means which can absorb the moisture and become very sticky. It is also called deliquescent, and opposite to deliquescent is efflorescent, the substances which will lose its water content and becomes dry, efflorescent. And then it has to be unreactive. So these are all the important characteristics of the calibrants used in the differential scanning calorimetry. Taking the metals, indium, tin, aluminium are the important metals to be metals which can be taken as the calibrants. And also the inorganic substances, potassium nitrate, potassium chlorate can be taken. The organic substances, polystyrene, benzoic acid, anthracene, these are all the substances that could be taken. So I have told you the important characteristics, and also I have given you some of the examples in metals, in inorganic substances, and inorganic substances. Now, what is DSC curve? The heat flux versus temperature. It is the curve. I've already shown you the curve. So this is temperature, this is heat flux. Heat flux versus temperature is drawn. Then enthalpy of a transition can be found out using the differential scanning calorimetry. Now, delta H, the enthalpy of transition, is directly proportional to the area under the peak. Look here, if you want to calculate the delta H, what is the area under this curve? See, a peak is going there. This is the baseline. What is the area under this curve? That area is proportional to the enthalpy change. In order to make this as an equation, a constant is introduced. This constant is called a calorimetry constant. In order to evaluate this calorimetry constant, you have to do the experiment with a known substance. A is the area under the peak, and this A is proportional to heat absorbed or evolved in a reaction. And the height is proportional to rate of the reaction. Look here, if more heat is absorbed, then the area will be so big. If the reaction rate is very high, then the peak will be of height. So these are all the information. So area is directly proportional to heat absorbed or evolved in the reaction. whereas height is directly proportional to rate of reaction. Now, factors affecting differential scanning calorimetry curve. Instrumental, and this side the sample. See, in instrumental side, furnace heating rate, recording speed, the furnace atmosphere, the geometry of the sample holder. Why geometry of the sample holder? It depends upon the surface area. Suppose if you are having a cylindrical sample holder, a spherical sample holder, the geometry will change, and accordingly surface area will change. And then location of the sensor, whether the sensor is close to the sample holder or it is away from the sample holder, and then the sensitivity of the recording system, and also the composition of the sample container, the material in which the sample container is made, that also plays an important role. Taking the sample into consideration, what is the amount of the sample taken, what is the nature of the sample taken, what is the packing. If it is closely packed, then that will show difference. And also solubility of the evolved gases. Suppose if the substance undergoes some decomposition and the gas is evolved, that evolved gas, if it gets dissolved in the sample itself, and also particle size. If the particles are of small size, then more surface area, bigger size, then less surface area, and heat of the reaction, and also the thermal conditions. So these are all the various factors affecting differential scanning calorimetry. So we have seen almost everything in the differential scanning calorimetry. Now